Well, thanks, Wei, for the very kind invitation. Pleasure to be here. Hello, everybody. We're going to take a step backward now in simplicity, because I'm going to talk about the use of MEG with simultaneous EEG. The rationale for this is that there are still many MEG centers in this country that record EEG, but do not model it. They only model the MEG. And for a long time, I felt that this is a mistake, that MEG and EEG are complementary. EEG has a lot of value to add to MEG, and I'm going to try to go through that today. Now, as far as disclosure, I am a member of the Medical Advisory Board of Compumedics. I have to admit I am a simple clinician. I have not invented any of the source modeling that I'm going to show you. My goal has been to try to determine ways to use these models most effectively in the clinical situation. So a bit of background. Let's see, get rid of this. Now, currently we have a variety of non-invasive localization techniques that are available, but only two. Only MEG and EEG are direct measures of epileptic pathophysiology performed in real time with millisecond resolution, and therefore can provide temporal sequencing of activity such as propagation. All the other measures, structural and functional, shown above, are secondary measures, secondary to the epileptic process. Let's start with EEGs. Long history, been around for a long time, and consequently has a lot of baggage dogma from the past. EEG evolved primarily as a pattern recognition technique. If you were famous, if you had a pattern named after you. Localization was secondary and only came later. And when localization did come using EEG, it was based on simplistic assumptions and techniques. Many of them, unfortunately, have persisted to the present. Few epilepsy centers have taken full advantage of the advances provided by digital EEG. We have to remember that although there are many wonderful new techniques, such as Dr. He showed us, the majority of epilepsy centers in the United States do nothing more as far as functional data, but look at EEG traces in longitudinal bipolar montages. That's it. So we've got a long way to go, and I've been trying to convince clinicians to adopt at least some of the simpler source modeling techniques that we'll look at today. Perhaps the biggest misconception is that the phase reversal in a longitudinal bipolar montage that everybody is taught is some mystical thing, whereas it only approximates where the negative field maxima may be, nothing else. And as I will hopefully show you, that is insufficient to do any form of source localization. Now, EEG, in order to identify, let alone model an EEG potential that is larger than the background rhythm, you need a fair amount of source cortex, about 10 square centimeters with synchronous activity. EEG can visualize gyral and fissural sources, but seldom sulcal sources because most sulci are not big enough to have 10 square centimeters without the opposite side of the sulcus being activated too, in which case the fields are canceled. EEG dipole models favor the center of activity but are deep to the source cortex because this little point source, a dipole, is trying to simulate the field produced by an extended area of cortex, and to do so, it has to be farther away from the surface. EEG is, however, sensitive to all source orientations, but perhaps radial somewhat more than tangential. So the EEG brain, if you will, let me get my pointer here. The EEG brain is really lissencephalic, no sulci, just convexity cortex here producing nice radial fields, as you see, or deep fissures, or such as the interhemispheric or the Sylvian fissure, as well as other gyral areas. The advantage of EEG, big one, is it's sensitive to all source orientations. It can characterize propagation fully because if something propagates from a radial source to a tangential source, it can still see it. Long-term recordings are available, and that enhances seizure capture. You can record EEGs for days, weeks. It's part of the standard epilepsy evaluation, and it's relatively inexpensive. Weaknesses in practice, however, are that many epilepsy centers, as I said, only review EEG in traces and principally only in bipolar montages. Everybody's taught to do that, unfortunately. Very few centers use voltage topography as an analysis tool, and even fewer use simple source modeling of spikes or seizures. MEG, however, has evolved more recently with little baggage from the past. From the beginning, source localization was always primary. Pattern recognition was secondary. Localization from the outset was based on spatiotemporal analysis of magnetic fields using source models such as dipoles. And from the beginning, head and brain anatomy was incorporated into both the head models and the results display. In order to understand the advantages and disadvantages of MEG, we need to remember certain principles. Whenever a current passes through a conductor, a magnetic field is generated around it, be it a telephone wire or a neuron. By the right-hand rule, point your thumb in the direction of the current flow, magnetic field wraps around it like the fingers of the right hand. If you have a bunch of cells lined up like these palisaded pyramidal cells, the magnetic field can add such that the magnetic field can exit the skull and come back into the head as well. Notice the orientation because that's important. If the cells are oriented parallel to the skull and scalp, if they oriented such as to produce a tangential field, then the magnetic field can exit and enter. However, if the cells are oriented radially to the skull, then the magnetic field tends to just go round and round into the head and not exit and enter. This is a problem that we'll talk about more later. The advantages of MEG are distinct. Biggest one is the magnetic fields are not attenuated or distorted by the skull, unlike EEG, which is. Simple head models accordingly work. There's superior spatial sampling because modern MEG systems have 200 to 300 plus sensors, and versus 10 times fewer number of EEG electrodes. It has superior sensitivity and can see smaller sources if they're tangential. Therefore, the source modeling accuracy can be sulcus or gyrus sulcus specific rather than a larger area, and superior frequency sensitivity because it can go from DC to gamma. Spatial sampling advantages are obvious. Here's a 25-channel EEG electrode array versus a typical MEG array with 300 sensors. Sensitivity, MEG can see smaller sources, about half the size of that of EEG. It's sensitive to tangential sources, as I said, plus or minus 45 degrees. Then it drops off. MEG can visualize activity on one side of a sulcus or fissure or tangential plane if unopposed. But just like EEG, if both sides of a sulcus are active, the MEG signal is canceled as well. MEG is not affected by the volume conductor, as we said, and therefore source models more accurately reflect source depth. But for large sources, it can favor an edge of that source. So the MEG brain is very different. Only deep sulcis and fissures are shown here. Certain tangential planes, however, certain gyral planes, however, such as the base of the temporal lobe and the tip of the temporal lobe, also produce tangential fields and MEGs. But notice that the gyral cortex is not illuminated here because MEG requires these tangentially oriented sources. So a area of cortex such as the superior temporal plane produces a very nice MEG signal. It's a very tangential in its orientation. But what about this complex area of cortex, since epileptic foci often involve some area? Well, for both MEG and EEG, activity in these sulci cancels out because they're opposed in orientation. EEG tends to see the remaining gyral cortex and in this radial field, whereas MEG would see this activity in this deep fissure unopposed. So on one side would see this tangential field. So you can see they can see different aspects of the epileptic focus. Disadvantages of MEG, the biggest: insensitive to radial sources, less sensitive to deep sources. Because you can only see radial sources for the most part, less capable of characterizing propagation fully, because if propagation turns radial, it disappears. Duration is limited. Most people can only tolerate an hour or so, an hour or two in the helmet. Therefore, fewer seizures are recorded. It's more sensitive to environmental artifact, often requiring, or mostly requiring, that expensive shielded room. And expense, an order of magnitude greater than an EEG monitoring system. Here's an interesting slide that the MEGers don't like to talk about. We have modeled here the confidence volume of the source solution, and this is how confident are you in your solution versus the orientation of the source. This is a simulation study that was done. If we have a source that's 15 millimeters below the surface on EEG, you can see that it really doesn't matter to EEG what the orientation is. The goodness of the solution is just about the same. If the source is a little deeper, 30 millimeters, EEG source confidence volume is a little better, but still it really doesn't care about the orientation. If we have a superficial source with MEG, no question, if it's tangential MEG, accuracy is fantastic. But watch what happens as the source orientation changes toward radial. At about 45 degrees, MEG and EEG solutions have about the same confidence volume. But as a source becomes more radial, MEG's confidence volume increases tremendously. The source solutions are no good with MEG. It really can't see it. More importantly, if the source is deeper, like 30 millimeters, MEG starts out with no advantage over EEG. And again, once you get, then it quickly loses that advantage as the source becomes more radial. So anybody who studies just MEG alone is sacrificing a lot of sources here that tend to be more radial in their orientation. Other weaknesses of MEG in practice, as I said, although most MEG centers record EEG, few of them model the simultaneous EEG. Many don't at all. Many MEG centers also model individual spikes and place emphasis on spike clusters. And even some, very few fortunately, assume that the size of the cluster is related to the size of the source, when in reality it's related to the noise level of the various signals. The bottom line here is MEG and EEG are complementary. The weaknesses of one are the strengths of the other. As far as volume conductor, MEG has the advantage. It doesn't care there's a skull and scalp there. Spatial sampling, MEG. Many more sensors for the most part. Temporal sampling, EEG has the advantage, not on the short side, but on the long side, days to weeks of monitoring. Source areas, smaller areas for MEG. Radial sensitivity is in EEG's field. Tangential is in MEG's. Deep sources, EEG can do better. Complementarity, that's the key of these two. Now, what we like to do, what we want to do as clinicians, is we want to know where the source of the spike and seizure activity is in the brain. And in order to determine sources, we need some form of biophysical model. Dr. Hare went through all of the many that are available. I'm going to stick with the simplest, the equivalent current dipole, where the voltage or magnetic field at any one moment is modeled by the best fitting single dipole. Clearly unrealistic, it's a point source, but it's easy to use and easy to interpret, and is the most commonly employed model clinically, particularly among MEG centers. Now, it should be known right away that most epileptogenic sources contain both tangential and radial field components. And the MEG is going to reflect principally the activity that produces the cortex that produces the tangential fields, and EEG reflect preferentially the activity of the cortex that produces radial fields. So you commonly see this sort of thing. Here's a MEG spike, here's an EEG spike, simultaneously recorded. Here is the MEG field. The fields are very tight, very small area field. This is the MEG solution to this. Up here in the cortex where it should be tangential orientation, that's fine. Here's the EEG solution, or the EEG field of the same simultaneous spike. It's quite broad. And accordingly, the single point dipole is sort of deep. However, if you orient the head to look at the dipole head on, you can see that the EEG dipole is pointing to the same cortex that the MEG is modeling. So these two are essentially seeing different aspects of the same source, and that is the most common scenario. However, MEG, most patients have both EEG spikes and MEG spikes. However, source models of MEG versus EEG commonly differ, often by orientation, since MEG sees only tangential, often location, they can be millimeters or centimeters apart, and timing, that's very important. MEG can either lead or lag, EEG vice versa. Confidence volume, MEG is usually smaller, principally because of the much greater number of sensors in MEG. So I'm going to concentrate on 6 scenarios here to show you the complementarity of MEG and EEG. We're going to look at situations where the MEG sees a tangential field, EEG sees a tangential field as well, same orientation. The two spikes are synchronous, and then the question is, what does EEG add to MEG? Well, in this situation, tangential fields seen by both in synchronous, bottom line is EEG doesn't add anything, mainly because MEG is really very accurate with tangential signals. Here are simultaneous spikes. Here's the MEG fields. Here's the tangential EEG fields. Here is the MEG dipole, nicely located in this remaining temporal lobe tip in somebody that had a partial temporal lobectomy. EEG dipole is in the area, but not in the brain. In this case, superficial rather than deep, because this person has had a surgery and has a skull defect, which is another problem, as we'll see with, as we said, with EEG. Now, what about if the source is tangential in orientation but very small? Well, EEG can't see really very small sources. So here's the situation that's commonly talked about, even though it's not that common in reality, where there is a MEG spike and no EEG spike. Here's simultaneous recordings. Here's 1, 2, 3, 4 nice MEG spikes, and there's really nothing down here that would knock your socks off in EEG, even though there maybe is a very mild, weak EEG field. Here's the nice, strong MEG fields. And the situation here was the person had a very small focus in this remaining temporal lobe tip here in the superior temporal plane, which was a great area for producing the MEG spike. So MEG spikes without EEG do exist, even though EEG is sensitive to all source orientations. If the source is small, and EEG may not see it. As I said, the most common situation is that MEG sees a tangential field, EEG sees a radial field, and they're synchronous. Well, in this case, at least EEG adds knowledge that there is a radial component. Synchronous spikes, here's the synchronous fields. MEG sees this tangential activity in the temporal tip. EEG sees this radial activity. The clinical interpretation of the two are the same. They're just seeing different components of the activity produced by the cortex. But what goes around comes around. This is what the MEGers don't like to talk about. If there's many more situations where EEG sees a radial field, MEG can't see it. In this case, EEG provides both the location and the orientation of the source. Here's a nice EEG spike with hardly anything on the MEG, and what you do see is not a very tight, very good field. This is a radial spike coming right out from the lateral temporal lobe, produced by this convexity cortex, not seen with MEG. So when MEG and EEG fields are synchronous, source characterization must be a synthesis of MEG's more accurate dipole location and EEG's more complete dipole orientation. However, when the fields are radial, there may well be no model-worthy MEG field, and only with source EEG can you get a localization. Now, what about timing? Timing is important too. Let's take a situation where MEG sees the tangential field, EEG sees the radial, but MEG leads. In this particular case, EEG only adds the radial component of the propagation because it doesn't really see the source. Here's a nice EEG spike, nice radial EEG field. Here's a nice radial EEG dipole. It's deep, pointing up to this cortex, probably modeling this frontal opercular cortex out here because that cortex has the appropriate orientation for this MEG EEG dipole, which is typically deep. However, here is the MEG spike, 20 milliseconds earlier than the EEG, and here's the MEG dipole. Well, it is in this Sylvian fissure. It is modeling this frontal opercular aspect of it very nicely. Here's the EEG spike. How do you interpret this? Well, this is the source, and the source probably propagates out into the more lateral opercular cortex when the EEG sees it. But the MEG provides the source. EEG shows you that there is propagation. But the other way around exists as well. MEG sees a tangential field, EEG a radial, but the EEG leads. In this case, the EEG provides origin and the radial component. Here's the MEG spike, nice MEG field, nice localization here of the MEG in the superior temporal sulcus. Little clinical pearl. Superior temporal sulcus is the deepest sulcus in the temporal lobe, and it is the only sulcus within the temporal lobe that will produce a reliable MEG field. Otherwise, MEG usually sees the tip or the superior temporal plane or the base. But here's the EEG. Again, 20, 30 milliseconds earlier, it sees this radial field from the inferolateral cortex, and you put the two together, and what you have is propagation from the inferolateral cortex in and around into this area of the superior temporal sulcus. But in this case, EEG leads, and it is the source. So when MEG and EEG fields are asynchronous dipole models of the leading field, define the source, while those of the lagging field help to characterize propagation. So in 4 of the 6 scenarios, EEG adds to the completeness and accuracy of the spike interpretation. And in 2 of the 6, it provides the localization of the spike. So no question, MEG and EEG strengths are complementary. So it makes good sense always to model the EEG with the MEG. Now, clinically, does this pan out? Well, it does. And a few years ago, Michael Wagner and I wrote a paper about the benefits of modeling both MEG and EEG, which we always do at the Overlook MEG Center where I work. So we looked at 3 years worth of recordings from 300 patients. We identified MEG and EEG spikes in both separately, and we created spike types. A spike type was a spike, either MEG or EEG, that had a recognized, it had a defined and distinct field topography. And they could either be MEG alone, EEG alone, or MEG and EEG together. And what we found, what I think is very important clinically, and that is in 42% of spike foci, these guys in here, in 42%, MEG and EEG provided complementary information. In most of them, the orientation of the two sources were different. In a smaller number, there were tangential in both. But 42% of the time, we got complementary information in both. 17% of the time, these two here, where there was either only a MEG spike or the MEG spike was leading, in 17%, MEG provided unique and critical information. What's underappreciated is this. In 41% of spike foci, EEG provided unique and clinical information. And on about a third of spikes were only seen in EEG, and 5% VEG leads. So if you eliminate all these all these spike foci from your analysis and only study MEG, you're really eliminating a third of the information that you have. So what are the indications for clinical indications for source modeling? Well, there are two principally ones, and the two that are reimbursed as well. Pre-surgical epileptic evaluation, focus localization is really key. In my mind, it should be a routine part of the evaluation of patients. If you have a MEG center, use it. If you don't, do EEG source modeling. As you can, get both. Certainly, whenever intracranial EEG is considered, you need to do this form of source modeling. You don't have enough localization information. That's why you're doing the intracranial study. So try to get more information non-invasively, just as Dr. Harris said. That is very, very, very important. Also, if you have a tumor epileptic focus near eloquent cortex, motor or sensory, you need to know where one is relative to the other if you're considering a resection. So source modeling is important for this situation as well. There are special niches for MEG, and those include evaluation of patients with confusing EEG fields, particularly tangential. If your center only uses bipolar montages, tangential fields are going to screw you up every time. They can't be interpreted with bipolar EEG. Pre-surgical evaluation of patients with skull defects. As we saw, skull defects can distort the EEG. It doesn't distort the MEG. Reevaluation of epilepsy surgery patients. Epilepsy surgery failures. Not only do you have a skull defect, but you need to pinpoint what epileptogenic cortex is remaining around the existing surgical lesion, or is there a secondary focus? Evaluation of patients with multiple or large lesions. Multiple lesions like tuberous sclerosis, which one is the bad guy? Large lesions, which part of the lesion is producing the epilepsy? Again, requiring the accuracy of MEG. And focus localization, as we said, near sensory motor cortex, you need to know where the focus is relative to it. So here's a typical example. If you had this EEG and you only had it in bipolar montage, I'm telling you, it would be difficult. Even in referential here, you have negativity on one side of the head, positivity on the other side of the head. Where is the focus? Is the focus over here under the negative situation like we're told? No, this is the classic false lateralization. And Meg very nicely says, oh no, the focus is really in this interhemispheric cortex here by this large resection site. It's not over here on the left side. Special niches for EEG, indeed. There are a lot of big bifrontal spikes that have a radial distribution, this bifrontal spike wave. They're often sometimes synchronous, or sometimes they're not, and there's secondary bilateral synchrony. It's not really a generalized phenomenon. It's a focal phenomenon with propagation. MEG, unfortunately, does not see these huge radial spikes, but may only see an asymmetrical tangential component and misses the predominant radial component. And this may be in the wrong place. So you can't just use MEG. Here's a beautiful frontal spike, nice big broad frontal field, right frontal field. And indeed, the MEG dipole is deep, but points nicely to the right frontal area. MEG sees a big signal as well, but the fields stink and the localization doesn't make any sense. So big frontal radial spikes you can't model. You shouldn't model with MEG. You're going to get confused every time. Poor indications for either. Yes. If a person clinically and EEG-wise and every wise you think has generalized epilepsy, don't do source localization in the hopes of finding a surgical focus. You're not going to find it, and if you do just MEG, you may make a mistake because MEG sometimes will show you these asymmetrical tangential activity and miss the whole bilateral radial activity. In multifocal epilepsy, if you have multiple foci on EEG, don't do these studies in the hope of finding one focus because there's not. You're going to see multiple sources as well. And finally, a statistic that's not well known but is valid. If you don't see any spikes on EEG with long-term monitoring, if you record a day or two, particularly at night during sleep, and see no EEG spikes, what is the likelihood that this patient is going to have an MEG spike that's not seen on EEG? It's not zero, but it's low. It's about 10%. About 10% chance of having MEG spikes without EEG. You need to know this statistic is low, but as always, sometimes it pays off big. Here's the patient's EEG. There's absolutely nothing on it as far as spikes are concerned. Here's the MEG spike, spike, spike. This person has MEG spikes without EEG, and this person has this mesial frontal MEG focus. So sometimes it pays off big, but realize it's 9 times out of 10, you're not going to find anything more. So bottom line, what I wanted to point out was that MEG and EEG strengths are complementary. If you source model both MEG and EEG, you can characterize more fully spike and seizure sources and any subsequent propagation. Source modeling either MEG or EEG or both should be considered in any epilepsy surgery candidate, more than considered, should be done if possible, particularly if an invasive EEG study is likely because you need that additional non-invasive information. So thank you. That's my clinical talk.
Thank you, Dr. Ebersole.
Happy to answer any questions.
Yeah. So let's have a Q&A session. If you have any questions, please type your questions in the chat area. All right. So do you think that the full head coverage of EEG electrodes, including covering the lower part of the temporal region and even the facial area, will that help improve the detection of the tangential dipoles in EEG?
Well, it'll help the detection of everything, including the radial ones. Yes, 10-20 electrodes are inadequate. Standard 10-20 electrodes are inadequate, mainly and principally because there's no southern hemisphere coverage. and the slide that I often have in my lectures wasn't in this one, is that the orbital frontal cortex, nearly all the temporal lobe, and a lot of the occipital cortex, basal cortex, are below the equator, are below the temporal chain of subtemporal electrodes. So subtemporal electrodes are absolutely necessary. I would imagine that greater than half of temporal lobe spikes and seizure activity is principally seen from these subtemporal electrodes. And if you don't have those, you're going to miss a lot of things. Your source models are going to be crazy. Yes, the more electrodes you have, the better. The problem is a practical clinical one. So you have to have, bottom line is, as agreed, as the IFCN has stated, and I totally agree, 25 electrodes are minimal. That's 19, 10, 20 plus 3 subtemporal electrodes on both sides. T1 and T2 by themselves, inadequate, not adequate enough. You need at least 6 subtemporal electrodes. More, better, there's no question. 32, better than 25. Where does practicality and theory cross? Probably less than in the high 40s or 64 electrodes. Does really high density, hundreds of EEG electrodes help? That I am unconvinced of, and if somebody has some nice data and would like to prove me wrong on that, I'd be glad to look at it. But at least clinically, definitely 25. If possible, in our pre-surgical patients, we used a 49 or 50 channel montage with collodion, but that took 2 hours. Yes, it took 2 hours for the tech to put that many electrodes on with collodion, but that's what we use for our surgical candidates. For diagnostic candidates, I think 25 electrodes with six subtemporals are fine. And if you do have and use high density electrode nets, etc., that's fine as well. Your problem there is usually limited to duration. You really can't record for hours easily. You can't record with sleep easily, with nighttime sleep easily. So bottom line answer is yes. The more electrodes, the better, at least definite subtemporals.
Second question, how can missing the radio sources affect research MEG data?
You'll have to ask the MEGers that, or the people who I consider myself an EEG or MEG or both. But the answer is yes, you have to take that in consideration. They're not seeing cortical convexity activity. I showed you, or they're not seeing it at all, or they're not seeing it accurately as that demonstration showed you. Once you get beyond 45 degrees from tangential, your sensitivity decreases dramatically. And yeah, certain things that they can't see. Fortunately, research on the Heschel's gyrus, superior temporal plane, auditory system, yeah, produces great tangential fields. Central sulcus produces great tangential fields, so sensory motor cortex, etc. Visual cortex, mesial occipital cortex produces great tangential fields. So a lot of the sensory areas produce nice tangential fields. But if you're dealing with the primarily gyrocortex, as you often are with a lot of epileptic spikes, then there's a problem.
All right. Last question. So, in your opinions, that's actually from me. In your opinions, the issue with the EEG is more about the coverage of the EEG electrodes over the scalp, or it's because the density of the electrodes? It's which one is more important?
Coverage.
It's the coverage. So
I mean, the bottom line is clinically, in non-surgical candidates, 25 electrodes is fine. But those 6 subtemporals are more important than a 10-10 coverage of electrodes of just the northern hemisphere. I would take the 25 with subtemporals over any 10-10 of northern hemisphere only.
There is a theory about the spatial sampling. As for the signal processing, the temporal signals also have this Nyquist filtering issues. You need to double the sampling rate in order to capture the real signals. And same principle applies to the scalp spatial sampling. Do you agree with that? That's an indicator that you need more electrodes than.
I think, look, I'm a clinician. I'm not a theorist or a scientist. But however, I'll make this analogy. If the skull and scalp were a perfect conductor, that is to say, if there was no alteration of the EEG signal by the skull or scalp, then I would agree that I would agree with that theory that the denser array of electrodes would be beneficial. However, if clinically you, and this is it's often said that high density EEG is just like MEG because it can see better. If you look at the size of MEG waveform of MEG fields, particularly of epileptic spikes, they're smaller, but they're not that tremendously small. So I don't think I don't think that theory holds that theory in practice holds water because of the smearing effect of the skull and the scalp. I don't think there are many meaningful, high frequency scalp, high spatial frequency scalp signals, at least in the clinical realm. For evoked potentials or something with a very small known source, that may be true, but for at least clinical sources, particularly epileptic sources, I don't think that there are a lot of really high frequency, high spatial frequency information that is there. That's my opinion. Not based on any theory, just practice.
Thank you. Thank you very much. We are happily over time, but I think everyone really enjoyed the talks.